Yeah, I know. I'm going to ask anyway. Is there any way to get a presentation view on the screen?
Good question.
If it, I'll manage it. If not, but every once in a while I look at my because I forget things.
Yeah.
So I'll look at my notes. I don't read from them.
Things change a little bit.
Yeah. Yeah.
Normal. I studied that's just those are for Brad. Is it under slideshow? It's not crucial. On energy.
Because I don't know anything. So I think yeah. How are you?
Oh, my old sailor bones are just gonna smell.
Your what?
My old sailor bones.
Oh.
They started aching.
There is snow with work past in the next.
See? Your old bones. It's gonna be right.
Honestly, I don't know why bother. People even bother to figure out anything.
Why never went to
I was wondering, what's turning on the lighting?
Are you?
It's gonna be.
Okay.
Okay,
It was not, but it's.
It's like just for you, like.
anybody. Like,
I mean, I don't think anybody would care, you know, I feel like it's restaurant style. You come and
Okay.
eat your.
It's okay.
Alright,
Cool. All right. I can sort of, in fact, well, I guess I want to. What about this?
Yeah, this one you did. Anyway.
Yeah, I guess that's right.
Are you planning to hang out back here? Or are you?
Yeah, you can put it, you can put it,
I can direct the camera any direction, so that's up to you. I don't. Okay.
Yeah. I'll do that.
Okay.
See it.
Yeah.
Good, how are you? Get a haircut?
Oh, last week already.
Last week, sorry, I missed the haircut. I didn't notice.
Yeah, you know, the half year was over.
The half year, you do it every 6 months?
Has to be worthwhile, right?
Yeah.
Well, it's an investment.
Yes. I normally do it every semester, but I have different hair every day.
Yeah.
I agree. Yeah. That's just it.
The authors.
Am I supposed to stand here?
Oh, so.
I don't know. I mean, I have no idea what they can see.
Very mostly look at the current. If anything,
Yeah.
Start. Okay, so welcome everybody to today's colloquium. It's a great pleasure for me to introduce today's speaker, Brian Saam. He got his PhD from Princeton in 1995, working with William Hopper and Gordon Cates. And he was working on spin polarized noble gases, including the first application to lung MRI. That's actually quite a famous publication. After that, he went to to Washington University in St. Louis as a postdoc, furthering his MRI work. And after that, he spent 17 years as a faculty member at the University of Utah. He moved to WSU in 2017 to chair the department. And his research is on optical pumping, spin polarized gases, with applications including things like magnetic resonance imaging. Okay, very happy to hear your talk today.
Thank you, Peter. I really appreciate it. Let me get right to it. Let's see what's this one. Did it stop working? There. Oh, I gotta say it's down. Down. Okay. So let me just start right away with my thank yous, because I don't want to omit them and rush through them at the end. I've been here for 5 years. And first of all, I'm grateful to the department for allowing me to come here, for bringing me in, and for giving me the opportunity to kind of rebuild the equipment and the labs that we had a chance to do. This really, I think everybody who's been in the group at one time or another is pictured here. I'm really proud of these folks. Shung actually was my first postdoc, and he built the lab, helped me build the lab in large measure. And he's now a faculty, research faculty person at Beihang University in Beijing. Trevor Foote, who's here, helped, and David Morin also helped build the lab early on. And Trevor is now a graduate student at Cornell, and Shmitri is a graduate student at Rochester Institute of Technology. They all did their theses in the group. I'm really grateful to Adnan also, who's my current postdoc, and to Zara. They've worked on, I mentioned them specifically because they've spent the last year and a half working on what I'll come to at the last part of my talk. And it's been a lot of really horrible systematics and things to work out. And now we got it working. And so I think there's a bunch of low-hanging fruit that's going to come out of that. So that's really exciting. So I just want to say I've learned something from all of these people, and I'm grateful to all of them for being part of the group. So I remember even a few years back, I used to get asked, are you a quantum physicist? Or you would hear people say, described as a quantum physicist. And I would say, well, yes, I'm a quantum physicist. I'm also an electromagnetic physicist, a thermodynamic physicist, a Newtonian physicist. To me, quantum was a subject. All right, but it's clear as we go forward now, oops, go forward, not backwards, that, come on, there we go. All right, it's clear that quantum has become a topic itself now, almost a subfield, the second quantum revolution. We have quantum computing. In our own department, we have the Engels lab doing this beautiful work with ultra cold atoms. And even now, I'm starting to get involved in experiments that have to do with quantum sensing. So this has to do with Rydberg atoms and the ability of Rydberg atoms, which are these single electron atoms where the electron lives way far away from the nucleus, right, in n equals 50 or n equals 60. And you can imagine that in that state, if you're dealing with low angular momentum states, you get big electric dipole moments. And so that means these things are very sensitive to electric fields. And it's sensitive on the quantum level. And so that's what we're talking about here with quantum sensing, using Rydberg atoms. Now, all of these things have in common, at least in part, that they make use of alkali metal atoms. And those are my favorite atoms. Here's the sort of the group of them in the periodic table. And they're all characterized by a ground state that's an S1 half, where the 1 half comes entirely from the electron. It's a spin half. And then these two excited states we call D1 and D2. And these are strong transitions. These atoms are studied a lot right after the advent of quantum mechanics because these are strong electric dipole transitions. You can see them. They follow the basic rules of quantum mechanics that you learn. They have simple selection rules, electric dipole selection rules that say the orbital angular momentum has to change by 1. The total angular momentum, which is the spin plus the orbital, can change by 0 or plus or minus 1. Okay, if you look at a sodium street lamp with a spectroscope, you'll see 2 orange lines, and that's the sodium doublet. These things are all in the optical or near IR region, so they're easy to see, they're easy to detect with photodetectors and so forth. So they're nice, they're a nice system, and they participate quite a bit in a lot of different kinds of physics. Now, one of the things I'm fond of pointing out is that they are really simple systems. And if you do a calculation of an electron on a spring, now you know what an electron on a spring is going to do. It's accelerating, so it's got to radiate. So how does it radiate? Well, it radiates in the direction shown here, and you emit a photon if you're thinking about quantum mechanics. Interestingly enough, if you do a pure calculation based on the wavelength, it goes the lifetime of this, and you calculate the damping coefficient for this, just classically. All right, you get an expression that looks like this for the lifetime. And if you plug in the wavelength of whatever D1 or D2 transition you're looking at, you get within 10% of the experimental value. These things really do look a lot like electrons on a spring. All right, so the Coulomb potential at the bottom looks like a bolt. That's because any attractive potential at the bottom looks like a bolt. And it looks like a harmonic oscillator. And so we talk about things like oscillator strength for these transitions. How do these transitions mimic, or to what degree do they overlap the transitions that you see in pure harmonic oscillator? And the answer for these atoms is that a lot. They overlap a lot. Okay, so now I'm going to make the discussion a little bit more complicated. I do want to remind you, though, I'll be talking entirely about rubidium atoms or alkali metal atoms. I'm going to say rubidium a lot because it's the one we use a lot, but the discussion applies to all alkali metal atoms. These alkali metal atoms all have nuclear spin, at least the stable ones do. And most of them, except for lithium-6, are half-integer spin. And it goes back to similar arguments you have with electron shells applied to nuclear shells, why that happens to be true. But you remember maybe a few weeks ago, we had a really nice talk involving lithium-6 about degenerate Fermi gases. And so lithium-6 is the one that has a an integer nuclear spin. And so it's a fermion. The rest of the alkali metals, the stable ones, are bosons. So we're going to make this a little more complicated and start talking about the total angular momentum of the atom. And so this is angular momentum addition. I advertised a talk that would bring in a lot of basic undergraduate quantum mechanics. And so I've already defined the total angular momentum of this atom as F, and it's J, which is L plus S. And now I'm saying it's the ground state, so L equals 0. And I'm assigning I, the angular momentum, to the nuclear spin. So we're going to be talking a lot about F equals S plus I. Okay. So the Hamiltonian in a magnetic field, we always have these things in sort of tens of Gauss magnetic fields. They come from Helmholtz coils, tabletop experiments. And so here's the whole Hamiltonian. It's got the magnetic moment of the electron, which is much, much bigger than the magnetic moment of the nucleus. So this one dominates. And potentially it has this coupling term we call the hyperfine interaction with this coupling constant A. And this thing arises because there's a Fermi contact interaction at the nucleus. The electron, you remember this electron cloud in a 1s state has some finite probability density at the origin. So this thing overlaps the nucleus and it creates a scalar interaction that adds this Hamiltonian. So this is a really interesting Hamiltonian to play with. Oh, and I meant to also mention that for the sake of understanding our experiments, we create these ensembles in little glass cells like this. Okay, so the experiments I'll be talking about, you can think of these glass cells that contain a little bit of alkali metal in them. We heat them up, that makes a vapor, and then we can put other gases in there as we choose, depending on the experiment we're trying to do. Okay. So let's build this atom up using our basic knowledge of quantum mechanics bit by bit. Okay, so what if we only had the electron? So the Hamiltonian would be really simple, just negative mu dot B, and here's the magnetic moment of the electron. So most of you are probably familiar with the simple Zeeman splitting. If you think about a Stern-Gerlach apparatus, the Stern-Gerlach experiment splits the silver atoms into two paths because of the electron in the silver. Rubidium and alkali metal atoms are quite the same way. Their ground electronic state is spin 1/2. And so you can split the two energy states according to whether the moment is along the field or opposed to the field. And you get out an energy splitting that we can write just simply as h bar times some frequency. Now we call this the Larmor frequency. And if you go back to the Hamiltonian, it's equal to the G sub s, which is this Landé, which is this G factor for the electron, which is a little more than 2, the Bohr magneton, and then h bar. And so we call this thing the gyromagnetic ratio. If you apply a magnetic field, this is the frequency of transition between these two energy levels at that given field. And that frequency also happens to be the frequency at which the spin or that angular momentum will precess about a magnetic field if it happens to find itself at some angle to the field. Okay, and that has to do intimately with things like the Bloch sphere and quantum mechanics, where the transition energy, the difference in the two energy states amounts to the frequency at which you move Rabi flopping from one state to the other. Okay, so let's keep going. What comes next? Let's add the nucleus, but let's not couple them yet. All right, or I can say that the coupling is really weak. And if we do that, then okay, it's just two spins and they both have these terms that correspond to negative mu dot B. The electron term is much stronger. Okay, and so what ends up happening is I get something that looks like electron Zeeman splitting with this tiny little splitting that has to do with the nuclear spin. Now this example is for rubidium 87, which happens to be nuclear spin 3/2. So 2I plus 1 is 4. So I'm going to split each of these states into 4 states, and the splitting is going to be much, much smaller because the nuclear moment is about 1,000 times smaller than an electron moment. And I'm going to label the states as simple product states. Okay, if I use this notation, then I have here the first is the magnetic quantum number or the azimuthal quantum number of the electron spin, and then that same azimuthal quantum number for the nuclear spin. So all these are plus 1/2, all these should be minus 1/2 because, you know, cut and paste. All right, so these should have been changed to minus 1/2, sorry about that. And then they all have the same nuclear azimuthal quantum numbers to indicate that each of these is split. Okay, that seems pretty simple. Now I want to say right up top that it also is going to look like this if the coupling between, if that I dot S coupling is weak. Weak compared to what? Weak compared to the field. So really, I can never talk about fields that are arbitrarily small, but if I'm talking about fields out here, then I can add in that I dot S coupling as a perturbation, and the energy spectrum is still going to look something very similar to this. Okay. So now I'm going to go and add the coupling explicitly. And so here's the Hamiltonian, the full Hamiltonian again, and I'm using the example of rubidium 87. And I want to talk about where we're speaking. So this I dot S term basically adds energy splitting to this atom. Now we talk about the weak field limit. And so that's just the opposite of what we were talking about before. I said strong field, I said the coupling is weak. Now the coupling between these two is strong. And for example, that hyperfine coupling is about 6.8 gigahertz in rubidium-87. And even in a typical, sort of a 30 Gauss field that we would use in the lab, the Zeeman, the largest Zeeman term, the electron Zeeman term is small. So the magnetic field is the perturbation now. And what does that mean? Well, if you look, it means that this term, this I dot S term, if you remember from your undergraduate quantum mechanics, you can always write that thing as F squared minus S squared minus I squared over 2, law of cosines, right? And if you do that, you realize that this thing is diagonal in the total angular momentum states. So as soon as I introduce I dot S, then I get good quantum numbers that can be written as the two possibilities for F, which is 3 or 2. Well, 3 or 2 for the, sorry, that should be 2 or 1, right? If I do my angular momentum addition correctly, 3 halves plus 1/2 is 2, minus 1/2 is 1. So it should say 2 or 1. And the hyperfine splitting is large compared to the Zeeman splitting, unless you go up to laboratory magnetic fields that are on the order of a kilogauss or more, 10 kilogauss. You have to go even higher if you want the Zeeman terms to completely dominate. But down here in the low field limit, it looks just like Zeeman splitting, but now you're treating these as two separate populations. There's an F equals 2 that has a Zeeman splitting into 5 states, and an F equals 1 that has a Zeeman splitting into 3 states. Same number of states, right? 4 times 2 before. Now it's these 5 plus these 3. Still 8 states. Okay. And what you get is you get a Larmor frequency for the nearest neighbor transitions in these lines that looks just like the electron Larmor frequency, except that it's slowed down by the nuclear flywheel, right? So it picks up this factor of 2i plus 1, which basically means it's slower. And it's slower because it's got this nucleus that's carrying a lot of angular, this heavy nucleus that's carrying a lot of angular momentum that acts like a flywheel when you try to torque it. Okay. All right. So we look at this now, we keep going. And I come back and I say, here's the full Zeeman hyperfine Hamiltonian, the one that I love, the one that I like to play with. And here it is. What happens if I don't have one of those limits? If the magnetic field, now it's easy to do. It's 1 kilogauss field will put you in the range where those two energies are about the same. They're at least on the same order. So what do? All right, so if S equals 1/2, which it always does in alkali metal atoms in the ground state, right? Then the Schrodinger equation is exactly solvable. All right. And that's nice. I have to stay closer here. And how do you solve it? Well, you diagonalize the Hamiltonian. That's what you do, right? And here's the whole Hamiltonian, and we're going to diagonalize it. Let's we can choose any basis we want to do this. Let's just, for the sake of argument, choose the total angular momentum basis. So I've got all the nice diagonal terms. But if this energy is on the same order as this one, then this guy, because it has individual spins from the electron and the nucleus, is going to produce off diagonal terms in that density matrix. Okay, but you know what to do. It's determinants, and there's Hutch-Gordon coefficients to relate the one basis to the other, and you know how to figure all this out. And what I say to my students is, do it once, it's good for the soul. Okay, so, and it's, it's a long calculation, and it goes on and on. And mine was 25 pages. But at the end, you get this expression, okay? And it's complicated. And it tells you that, hey, you added something pretty simple, just a little Zeeman term to your hyperfine coupling, and you get a pretty complicated energy spectrum. But the first thing to notice is, look, at the lowest fields, it looks just like what we said when the Zeeman terms were dominant, right? In other words, here's F equals 2, here's F equals 1, and it looks like sort of standard Zeeman splitting. And at the highest fields, it looks just like what it looked like when we had weak coupling between this nucleus and the electron. In other words, it looks like Zeeman splitting of the electron with this little perturbation that produces a small splitting due to the 4 nuclear spin states, 3/2, half, minus 3/2. In the middle is no man's land. In the middle, you can't write down good eigenstates that are exclusively, one total angular momentum state or one total product state. So this is the land of product states where you identify them as electron and nucleus, and this is the land of total angular momentum. But it's really beautiful that this thing can be solved exactly, and that this is the structure that you get. And it's one of the reasons that we calculate things like the transition energies between these states so precisely. We know them very well, and that means we can think about using them to measure things like magnetic fields. If you know this trend, if you know the sort of the gyromagnetic ratio for one of these transitions, and you stick it in a magnetic field and you measure the precession frequency. This is what I meant in the abstract when I said physicists love to count things. We love measuring frequencies. And if we've got something that isn't necessarily purely a frequency, isn't it cool to convert it to a frequency and then measure that? Okay. All right. So like I said, it's a pretty complicated expression. You can expand this square root because x can be small if the field is small. And so you can understand sort of the first and second order field corrections here if you want to. And I just want to point out one of the things that this is really useful for is, or one of the things that comes up in is this cesium atomic clock. And I'm going to just present you a very simple explanation.
So before we move on, is there an explanation why that upper manifold has a straight line going down? It looks like it's different than the rest.
Why the,
So if you look at the 2 minus 2.
right, this thing.
Yeah, that's kind of cool.
That's the guy. He has to make the change. So here, he's considered to be part of this manifold, and he has to make the change to be part of this manifold. But what you'll notice, this expression is a function of m sub f. So although I can't tell you what the eigenfunctions are in the middle, I can certainly tell you that angular momentum has to be conserved, right? So the two have to add up. So m sub f is the same all the way through. And so you see, this is the one guy who has -2 for a total projection onto the z-axis, and stays -2 even for the product basis, where you just add -3/2 and -1/2.
Is that linear then? And where does that come
It's not, I don't think it's linear. You caught me, not much in here is.
Right.
And so, but I can't tell you for sure. Obviously, the way it's depicted here, excuse me, the way it's depicted here, it certainly looks pretty straight, doesn't it?
I was wondering, can you just look at that square root and wave your hands?
Maybe.
No, well, that's, you need to do it here.
Can I look? I did do it here.
Right.
Yeah. I mean, certainly it's going to be straight to first order at low field. How long it stays straight, or whether or not the additional terms are particularly small for some reason, maybe some interesting confluence of the numbers that go into it. I don't know. But okay. Speaking of atomic clocks. So atomic clocks make use of this thing. All right. And you can think of an atomic clock as like a pair of Stern-Gerlach apparatus. Okay. So these things are at high field, and you know from basic quantum mechanics that if you run a beam into a Stern-Gerlach, you get 2, one for spin up and one for spin down. And you also know that if you block one of these and you take this beam and you continue it through to another identical Stern-Gerlach apparatus, you still don't have the other spin state, right? It stays, these are all up, and it stays all up. But what if you make 2 such apparatus, but then you put a low field region in the middle where you drive transitions in this low field region between the hyperfine states? That's exactly what the clock does. And it uses this nice 4-0-3-0 transition. The magnetic quantum numbers are 0 because then they're least sensitive. The frequency is least sensitive to any stray fields or applied fields you might have in this region. And it has a very nice, precise frequency that drives it. And when you do drive it, what's going to happen is you're going to produce atoms that go into both of these manifolds. So when you come back to the high field Stern-Gerlach, you're going to start picking up atoms in the other spin state, of the electron spin state. Now, what do? You optimize this detection based on this frequency. You feed back using some voltage control or servo or something like that. You feed back the information from the detector to your microwave source, and you lock the frequency there. And then what you do, if you're smart, is you pick a frequency that's really close and say the second is defined by this number of oscillations of that transition. And so this number here for this transition is exact, right? And it represents the definition of the second. Okay? So it's accurate. I'm sorry that's out, but it's accurate to about 1 second in 30 million years. It's better now. Atomic clocks are getting even better. But the point is, this is what makes things like GPS possible, right? You couldn't do GPS without this. What did you have before? You had the rotation of the Earth. You had the orbital period in the tropical year 1900, right up until 1967. Imagine that. Hey, if an earthquake happens somewhere on Earth and the rotational period changes, there goes your definition of the second. All right. But this gives you a little bit more stability, right? Okay. So back to our story. How do I like to use these things? I like to do EPR spectroscopy with them. And we live in kind of this region, which isn't quite the extreme low field region. And so instead of having just one resonance line with one Larmor frequency, we live in a place where all of these transitions are split up into individual lines. This notation here is just using the mean azimuthal quantum number between the nearest neighbors to define the transition itself. So this is an EPR spectrum that shows peaks due to nearest neighbor transitions from this entire spectrum. The ones pointing up are from the upper manifold, and then the ones pointing down are from the lower manifold. And I'll say more about this later, but of course, these frequencies are exquisitely sensitive to the local magnetic field. I'm going to make use of that. Okay. But right now, I just want to point out that this spectrum occurs, it arises at all, because I have to produce some population imbalance in these states. Okay, and these energies are tiny compared to KT. So if the sample is just sitting there in the middle of the room, KT isn't going to distribute the population asymmetrically. I have to do something. And you can see I do something, because in this example, this is the largest energy transition that corresponds to this transition right here, from -2 to -1. And so there must be a lot of atoms here compared to what there are in the other states, because the transition peak is so large. And for those of you experts, this is a low flip angle type spectrum. This is a well into the linear regime, a weak RF excitation. So the transitions very closely represent where the population is. Okay. All right. Am I doing on time? Okay. Depopulation optical pumping. So this is what we do, and don't be afraid at this diagram. Here's that D1 transition I talked about. We're going to use this just as a pump. Remember, the atoms don't live very long in the excited state. They always come back. That's what these black arrows are. They always come back. So even when you have the laser shining on this cell, you're exciting this transition, the 5s1/2 and the 5p1/2, and they're always coming back. And the trick is you add a selection rule. So the selection rule you add is you use circularly polarized light, and that forces the transitions from all these hyperfine states to have a change in m sub f of either -1 or +1. In this example, it's -1. So we're pumping with -1, and there's only one sublevel out of which you cannot excite. And that's this -2, because there is no -3 in this manifold. And so it doesn't really matter. I could tell you all about the physics of how these states mix and Clebsch-Gordon coefficients, how they decay and what the efficiency is. Doesn't matter. If I pump out of these states long enough, a few milliseconds, then this guy becomes practically empty. And in fact, if I keep pumping I'm sorry, this guy becomes full, excuse me, not empty, becomes full, right? Because I can't pump the atoms out with the light So they, as I keep pumping, they accumulate in this state. I have a polarized ensemble. And polarization, I usually think of the electron polarization for reasons I'll come to. The electron is coupled as part of this complex hyperfine structure, but it's the one that does all the action when we talk about spin exchange. We'll talk about that in a minute. So we talk about the electron. And besides, in these states, the product states and the total angular momentum states are the same because they're the maximum states, right? So there's only one way I can make a 2 - 2 state. I have to have all the negative angular momentum from both the electron and the nucleus. Same with this +2. And if I just flip my quarter wave plate around, I can reverse all of this and I can pump into this state. The point is, I get a very asymmetric population. I get a highly polarized vapor in say 10 to the 15 or 10 to the 16 density per cc in the cell. And I go backwards. Oh yeah, just coming back here, because I wanted to point out that if I flip the quarter wave plate around, or if I use the other helicity of circularly polarized light, of course, then I would pump into all of these states and this spectrum would kind of flip around. And I'd have an intense peak over here at the 2 + 2 to 2 + 1 transition, okay? All right. So then the other trick that we do, the one that we get a lot of mileage out of, is this collisional transfer to noble gas nuclei, something called spin exchange. Look at this. This is cool. This is a rubidium and a xenon atom. They're 4 angstroms away, and it's a calculation of the rubidium valence electron wave function. All right, and you can see that, of course, it's got a large amplitude on its own nucleus. That's the hyperfine coupling. But it's also got a really large amplitude on the xenon nucleus. It sits on top. It's the same kind of coupling. It's a Fermi contact interaction with a coupling coefficient. It's the same kind of coupling that gives you the hyperfine interaction, allows you to transfer through this scalar interaction spin that's been accumulated in the rubidium system to the xenon system through kind of a mutual spin flip type thing when they encounter one another. Okay, so I end up with something called a hyperpolarized noble gas. And again, I use spin 1/2 noble gases almost exclusively. Xenon 129 is a spin 1/2. So polarization is very easy to understand. Number of ups minus number of downs divided by the total number. And so I can create orders of magnitude more polarized than thermal. And again, the energy differences are tiny. So you can go to huge magnetic fields. That's why when you do MRI, you got to go into the big magnet because they're creating a lot of proton thermal polarization. Okay. We do this in 30 Gauss. Yeah, Brett.
Clarify, that's a probability distribution for a single orbital of an electron, valence electron.
This is not a probability distribution. It's the wave function amplitude. So if you do a calculation, if you ask yourself, and I can't remember whether this is deformed wave or maybe it's WKB, how this is done.
It's
But
a wave function of a valence electron.
it's a wave function of the rubidium, of the alkali-metal valence electron over the whole range with the xenon atom this close, 4 angstroms away. And you see that you get a lot of amplitude on both nuclei, okay? And in fact, it's weird that you don't get much in between. But if you think about it, both these atoms have spherically symmetric cores of electrons. And as the electron penetrates a little ways, the exterior radius of that spherical core doesn't count anymore. And so it looks at the nucleus and says, oh, more positive. And then even more positive, it gets sucked in. Literally, it gets sucked in. That's true for the hyperfine interaction in the atom, and it's also true for this spin exchange interaction.
Which one has the highest work function?
Which one?
Which one has the highest work function, rubidium or xenon?
Work function?
Well, like if you want to ionize xenon.
Oh, xenon, right? Because xenon's closed shell. Like this wave function is strictly the valence electron of the rubidium. So the xenon electrons are being deformed by the interaction, but they're not.
That's why you're working with the rubidium, because that one is falling into.
That's right. And you can also add to that and say, hey, rubidium is this chemically really reactive thing, unless it's dealing with the noble gas, right? So you don't get a chemical reaction, you get this instead. Okay. All right. So so we shine a laser on the cell, and to polarize the xenon, the characteristic spin up times, we call them, is like 10 minutes. kind of slow for an atomic interaction. Tells you this is only happening during a collision, of course. So most of the time you're not in collision. It's a light limited process. So we can now make a liter per hour of hyperpolarized xenon. All right, and I realize that I have these last two bullet points on the next slide, and I forgot to delete them on this slide. So I just wanted to talk first about how it's done, and then give you a brief schematic and tell you that it is a light limited process, and the advent of these lasers, these high powered diode lasers, they're photon fire hoses. We don't really care about their spectroscopic purity. We just want the photons. And now that we have them, it means that we can produce, instead of the amount of gas in this small cell, I can produce larger amounts of this polarized gas, okay? And the longitudinal relaxation of the 129, that means its tendency to return to thermal equilibrium, which of course it wants to do, is relatively slow. It can be tens of minutes, it can even be hours under the right circumstances. So it's easy to build up a lot of this polarization and then use it for something. Now, it's also easy to turn the spin exchange interaction on and off, because in the oven, the alkali metal density, it's a saturated vapor pressure, and it's exquisitely dependent on temperature. So hot gives me a big density, changing it by 10 or 20 degrees decreases the density dramatically, and the spin exchange interaction turns off. So now the angular momentum is stuck in the nuclei. Okay. All right. So this is kind of what it looks like in the lab, just very briefly. This is the pump laser and the tube through which it flies. And here it comes in now to these Helmholtz coils, and there's an oven here that's kind of shown here. This picture also shows the probe laser. So there's a main laser that comes in. There's a probe laser that does Faraday rotation that's able to detect these hyperfine states by the precessing magnetization, changing the rotation plane of the light from the probe laser. We do this, we do our own cell making. This is our vacuum gas handling system for cell fabrication. The little cells come on manifolds that look like this. And then we seal them off ourselves after we distill in the alkali metal and put in whatever gases we want to put in. So there are a lot of applications to these gases. All right, they're in fun searches for physics beyond the standard model, co-magnetometry. They're in biosensing, because xenon is very biologically sensitive. It dissolves in tissue and so on and so forth. But the big one that you hear about the most is this MRI, okay? And so our collaborators, and by the way, our funding, I forgot to thank my funding agency, NSF. Our funding is a GOLI grant, which is grant opportunities for academic liaison with industry. And our GOLI partners is this company in North Carolina, Polarian, and this is what they're working on. And what you see here is, so this is what they've built. So it's a little different than our setup. It's this sort of dedicated machine that cranks out liters of xenon in an hour, okay? Polarized, right? But what you see here is there's a comparison in ventilation between a healthy person and someone, post-COVID. But they have these special contrast mechanisms that have to do with the fact that the xenon has a slightly different resonance frequency in the lung tissue and in the blood. And so what this is monitoring is the ability of the lung to move air through that barrier, through that tissue barrier into the blood. And you can see long COVID is real. Okay, that's what this is showing you. Now, I don't want to steal the thunder too much from my colleague Bob Streethouse, but this talk will be continued because he's coming to give a colloquium at the end of March. And he's the chief science officer of Polarian. He's the guy that is responsible for work like this. So anybody asks me about relevance, if I'm applying for a grant, I say, hey, COVID, there it is. All right. So that's coming at the end of March. Stay tuned. Let me finish up just with a couple of slides talking about what we actually do and what we've actually been doing recently. And the issue for our GOLI partners is, how do I make the most gas, the fastest, the cheapest? And one of the questions that's come up, interestingly enough, is which alkali metal, rubidium or cesium, it works best with xenon 129. What do we mean by works best? Okay, well, we have an equation here that's called the spin exchange efficiency. So if I can measure the spin exchange rate per alkali metal atom, okay, that's what's in the numerator, and divide it by the relaxation rate of the same spin in the same interaction due to all the other mechanisms, okay, actually due to all the mechanisms, including spin exchange, per xenon atom, then I get, and where A here represents either rubidium or cesium, then I come up with, and come on, okay, so there's the spin exchange rate, and there's the spin destruction rate. So I need to measure both of these to understand sort of the intrinsic, what this is really saying is, in one of these interactions, what fraction of the angular momentum that started in the polarized rubidium electron ends up in the polarized nucleus? That's what this expression is saying. And basically, to get at it, you need to measure both of these things. Okay, and that's what we do. The dominant mechanism for the spin destruction, I told you about spin exchange. The dominant mechanism for spin destruction is something called spin rotation. That means that, yeah, when the rubidium atom comes in, the electron can transfer its spin to the nucleus. It can also see a big current of electrons from the xenon as it passes by, which creates a magnetic field that's modulated by the collision that can cause the spin to relax. Most of it is that. Xenon has a lot of electrons. It's a potent destroyer of spin. This number is somewhere between 5 and 10% typically for a spin exchange pair. For one involving xenon. It's a lot higher for some of the other ones that don't have such a strong spin destruction mechanism. Okay. And I just want to point out too, before I talk about our work, that there's a lot of rich physics in the spin exchange optical pumping of xenon 129. So I've kind of talked about these things as encounters. And I've hesitated saying collisions. And that's because, oh yeah, there are collisions, there are binary collisions that mediate this physics. But there are also these beautiful van der Waals molecules that form, okay? Now, the upshot here is binary collisions, fraction of a picosecond, typically in duration. These molecules that need a third body to form, and it could be nitrogen, it could be another xenon atom, okay, it could be anything you put into the cell, just about. These things last maybe nanoseconds or tens of nanoseconds. And you say, well, that's still really short, it's not really a molecule. Self-respecting chemist would probably tell you it's not. But that's 3 orders of magnitude change in the encounter time. And you may remember from your basic quantum mechanics that there's an approximation that says when you're in this sudden limit, this limit of short interaction times, and even though this is a lot longer, it's still in the limit of short interaction times. The probability for something to happen, whatever's in the matrix element, goes like t squared, time squared. Give me 3 orders of magnitude more interaction time, I give you 6 orders of magnitude more probability that this is going to happen. Okay, and so these aren't very many in the population, but they're really important. They contribute a lot. And understanding this dynamics is really interesting too, because of course the lifetimes vary, there's a distribution of lifetimes. What happens when the electron comes in depends on whether the lifetime is long compared to the hyperfine precession period or short compared to the hyperfine precession period. Is it just the electron that's interacting, or does the electron recouple with the nucleus while it's interacting? None of this you have to worry about with these binary collisions. A few years ago, I was privileged to participate in writing a review article with Thad Walker and Tom Gentile and some others on polarized helium-3. And I went to Thad and I said, Thad, don't you want to do xenon too? And he said, no way. I said, I understand helium-3. It's just binary collisions. There's no molecules. But this is a lot more interesting in rich physics. And maybe I'll come to you in a few years and do a colloquium on how we've explored the spin exchange rates in different pressure regimes that produce different lifetimes of molecules. Okay. So how do we measure the spin exchange rate? We use what I just described, this atom, as an embedded magnetometer. So the same interaction that transfers the angular momentum to the nucleus can be used to monitor the polarization of that same nucleus, okay? This frequency, this precession frequency that I get by driving these hyperfine transitions is very sensitive to the local magnetic field. And in fact, there's the applied field, and then there's the field that comes from the spins. And all I have to do, and remember what I said, it's like, I'm interested in the polarization, but what I'd much rather do is measure a frequency. So here's what I do. I take this spectrum of EPR and I watch what the peak does in the presence of this polarizing xenon. So I look at the shift of the peak, the shift of the resonance frequency that comes about from the field that's generated by the polarized xenon atoms. In fact, they're all pointing in the same direction. And I can see this and I can measure it exquisitely. So here, and when these things polarize, they polarize like a charging capacitor. So that's this function right here. It's just a charging capacitor function. You have the polarization of rubidium, you can't get higher than that. And then you have a ratio of rates that sort of dictates, well, how fast are you filling the bucket versus the bucket is leaking away. All right, and then there's the actual exponential. And you can see that I can measure, by monitoring these kinds of curves, I can measure things like the spin exchange rate in here. Now it's a little more complicated than that. And I actually also have to measure the alkali metal density very carefully. And that's something we're doing in the lab right now that we're not quite good enough at yet to really say what the whole numerator is of this efficiency. But we've recently made, and I should say too, we can see sorts of variations from this field on sort of the tens of hertz level out of say 20 megahertz, which is our typical EPR frequency for looking at these atoms. So we're pretty sensitive and we can see this nice spin up curve. So we've also used this technique to characterize the coupling coefficient of the spin exchange interaction. And that's the papers down here, one that we published in 2019 and one that is submitted and in review now, talks about how we do that. Okay, where we have made very recent progress is with the spin destruction measurement, so the denominator of this. And I just want to take a moment and point out that this is a pulsed EPR spectrum. So we got polarized vapor, we deliver a pulse of RF that covers all of the hyperfine lines at once because it's short, so it has a big frequency coverage. And it gives us the whole spectrum in one shot. This is a single shot spectrum of rubidium-87. And I know that probably doesn't mean anything to you, but it means something to Adnan and Zara because they've spent the last 12 to 18 months figuring out all the systematics that were messing us up to get this absolutely beautiful signal to noise spectrum that we can now use, because it turns out that the electron polarization, the thing we're interested in, is proportional to the total area under this spectrum. So if I can acquire it quickly, and I do have to acquire it quickly because these relaxation times are going to be measured in hundreds of microseconds. So what I'm going to do is I'm going to use an optical chopper, right? And I'm going to turn off the pump light for a short period of time, wait, and this thing is going to decay. And then I'm going to pulse it and acquire. And, and I vary the time and I plot the intensity of this spectrum. And that tells me how rapidly the electron spin is being destroyed. Okay. And this technique, it's called relaxation in the dark. It's not new. It goes all the way back to Franzen in the 1950s. This is the first person credited with doing this sort of experiment. But it continues to be amazingly useful. And so the problem we have, again, we're dealing with this complicated atom. The problem actually is we have too many observables. So what do I mean by that? Here is a beautiful decay of the electron spin polarization as a function of time. There are error bars there, but you can't see them, all right? There's a beautiful decay, and we have to throw away most of it because it turns out that this is a multi-exponential decay. When you have an atom like this that has all these observables, S of Z, S of Z, I dot S, the quadrupole thing, all of these observables can have their own decay time constant. And if the electron has a role in all these observables, then it has time constants from all of them. It's even worse because it doesn't have to be true that there's a time constant for this and a time constant for this and a time constant for this. The actual time constants can be linear combinations of the observables. So it's a mess. Fortunately, the slowest time constant corresponds to the spin destruction of the electron in these, and I won't go into that, it's fairly complicated, but the point is that if I wait long enough, I can find a single exponential. So here it's showing you I had to throw away all this beautiful data until I get to about 4,000 microseconds. And here is where I have something that fits. Still a really nice fit. Okay. And you know, the way one does this, of course, is that you just by trial, you just keep taking away, eliminating points until the answer gets steady single exponential. You take that answer and you plot it. So now we're comparing this spin destruction. Come on. We're comparing the spin destruction, the slowest decay rate for rubidium versus cesium. And I've got to unpack this a little bit, but it's my last slide. Okay, I got to unpack this a little bit. So here, as a function of total gas density, most of the gas in our cells is helium-4. It doesn't play a role. There's a little bit, there's 3% that is xenon. Xenon is the actor. Xenon is the one that's causing this spin destruction. So as a function of total gas density, amagats are pretty close to bars or atmospheres. It's the density of an ideal gas at STP. Okay, so think of these as kind of bars or atmospheres, 3% of which is xenon. We get these red points for rubidium and the blue points for cesium under exact same conditions. These all represent individual vapor cells that we had to make with precise amounts of xenon in them that we measured at the same temperature and under the same conditions. And so the news here is that the spin destruction rate for cesium is maybe 20–30% smaller across this range. And we did this for a couple different temperatures too. This is 130 degrees, but it didn't change very much. So overall, we find that cesium has a smaller spin destruction rate. Now, what is all this stuff? Well, this is an old model by Nelson and Walker from 20 years ago. They did a similar measurement on rubidium. They had many more data points. Again, the error bars are underneath the dots. But this is a multi-parameter fit, and it's complicated. And it's complicated because there's binary here, there's molecular, there's diffusion of the spins to the walls. That's responsible for this turn at low pressures. But we took their model and they had 1% xenon, we had 3%. So we just changed that. And the red line is their exact model with our data. So we feel pretty good about it. And then we do the cesium and we find that it's 30%, 20–30% lower, depending on how you look at this. And so far, we've done a modification of their model, incorporating the physical parameters that are involved for cesium. And we see that, you know, we can fit a model, we can fit some similar model to these data. So there's an old result that we need to look at, that the cesium spin exchange rate is about 10% bigger. And if you throw that together with our results, it suggests that spin exchange efficiency that we care about might be as much as 40% bigger for cesium xenon versus rubidium. And that doesn't seem like it's too earth-shattering, but if you're boss at Polarian and you're trying to figure out how to make the most polarized gas with the least amount of money, and you got to think about laser technology and all that, it's important news. It's something that's important and something that we're right now in the process of writing up. Okay. And I see I'm right at time, so I'm gonna conclude, and I'll just say I don't do much in the way of conclusion slides. I hope I've convinced you that alkali metal atoms are a great playground for lots of really cool physics that you can do on the tabletop, but that also has great applications to things like imaging and magnetometry and this sort of thing. And I'll just thank you for your attention.
Thank you very much for this very engaging talk. Questions? Good.
Yeah, I was just wondering, maybe you mentioned it when we had those van der Waals molecules. Looked like it was initiated by a nitrogen.
Yes.
What's that about?
So typically in optical pumping, and I didn't get into the details, but what we do often is we need to incorporate a little bit of nitrogen into the cell. And the reason the nitrogen is there is that, I didn't talk about this, but when you excite the atom in the pumping state, that excited state returns quickly to the ground state. But if it emits a photon, the photon is unpolarized and it can screw up your optical pumping. So the nitrogen is there to de-excite that excited state collisionally. So it quenches the state without it emitting a photon. It also so happens that if it's there, it can be the third body that that is present to form the molecule. It has a cross section for doing. It's not that different from xenon. Helium has a measurably smaller cross section for being the third body. We have all those gases present in typical cells.
So the third body thing, so it's like an momentum conservation, an energy thing.
It's an energy. That's right. Something has to. There's no direct way to get the well populated with some quantum state. There's no tunneling. That's what I should be saying. You have to have a third body to take away some of the energy to the form of balance state.
Just a fitting question. Your data is so clean. Why didn't you just do a multi-exponential fit as opposed to taking data away and trying to get it to be?
Yeah, that's where I'd like to go there. And I'd like to go there especially because, of course, at high polarizations is where we do spin exchange. So the rates right there where there's the collisions are going on is where we do it. It turns out the theory is gory, right? And so that's probably the first reason we didn't do it. Is that
do multi-exponential with parameters, don't worry about the theory.
That's right. And see what falls out.
Yeah.
And I think that's something we could try. And I think we're now getting to the point where we have good enough signal to noise that it might actually work.
I think it's always better to fit with less fitting parameters. So it's always good not to have the human being put in their bias by deciding where to chop off the line.
Oh, yeah, no, that's exactly why.
Fair point. Fair point. Yeah, and I mean, to the extent that we can really get the data as precise as we want it, because I'm always worried about, well, 4 free parameters, you can fit an elephant, right? So I'm always worried about that. So I want to make sure that we're getting the data precise before we engage in that. Yeah, that's a great question, though.
So in terms of applications, is xenon the way to go, or does helium still have a chance?
Xenon's the way to go. And that's pretty definite now. Helium, first of all, even if you recover as much of it you possibly can, it's not cost effective. It still escapes. I mean, we're losing helium-3. It's first of all, it's rare, right? Helium-3 is not balloon helium. So it's some small, tiny little fraction of helium that you get out of the ground. Xenon, of course, you get from distilling the air. It doesn't leave. So it comes back. You can enrich it to xenon-129 pretty easily. It's about 26% naturally abundant. But the big thing is that it's most biologically active. So helium-3, basically you can tell where the gas phases are inside the lung. But with xenon, it dissolves into tissue, into blood, and then it changes its resonance frequency for you. So it says, hey, I'm in blood, and then you can image that as well. And that's what those COVID images were showing. We're showing actually separate images in different compartments of the gas phase, the tissue, it's called the lung parenchyma, and the blood. And that really is potentially useful for doctors. Whereas the ventilation images, it's a great showpiece when we first started doing this because the helium-3 moment is so big. It was easy to get really nice, bright images. I used to say it was like, Monday Night Football. What are you asking about? It's football on Monday. It's like, it's an image of a lung. What else do you want to know? When we first did this, that's 20 years ago. But now I think really it's very clear that xenon offers much more clinically in terms of what it does and how it behaves in the body compared to helium-3.
So then these images, were they taken with just regular MRI machines?
Yes. Yes, they are. I mean, the companies now provide packages for these nuclei that they didn't have when we first started doing this. We used to jury rig together these kinds of coils and things that translated frequencies up and down so that we would fool the machine into thinking it was imaging protons. And now, of course, Siemens and Philips and all these companies, GE, provide packages for imaging the noble gases, helium-3 and xenon-129.
But they're standard MRI machines.
Standard MRI machines, which are now 3 Tesla.
Yeah. All right.
Okay.
Any further questions? Otherwise, let's thank Brian again for a fascinating talk. All right, awesome.
Thanks.
Very nice.
Feel like we're just now on
Awesome.
Sorry it took this long. It just took what it took.
I still remember you, it's like 10 years ago. That was a group.
Well, and the thing that I, the thing that I noticed too, is that the thing that I didn't understand. I knew that was the problem. Because you immediately come to a situation where you don't have a progression of people. Everybody's just and even the advanced people are still teaching them to do it. So that's really possible.
Yeah, part of it is the spectral